Θα τρελάθηκε αυτή να σου λέει, τώρα μου λένε ψέματα. Αλλά νομίζω ότι
Okay, guys, my name is Kao. And I'm doing some lesson with it now on propulsion for steam for LNG vessels. Now I'm a marine engineer, chief engineer, steamships and motor ships combined. I've been working at the college for a number of years. I teach senior marines, general and ship construction and motor. So could I just ask you, what's your experience? Your name, please.
My name is Nisha. Nautical science graduate.
Nautical science. Yeah.
Doing
so you've been to see?
Cadet. The cadet.
Yeah.
Cadet only.
What sort of ships did you sail on?
ACC, Tanker, A7, container ship.
Okay.
Chemical tank.
And these were all diesel ships?
Yes.
Diesel propulsion?
Yeah.
Single propeller?
Yes.
Yeah. Okay.
I worked as a physics supervisor for a year. Now I work at university as a teacher.
Okay. So applied?
No. Federal King Abdulaziz University.
Right.
I'm doing my PhD.
Right. Good.
My name is Muhammad. Almost as Hisham, I served for 1 year as cadet, both tanker, container, through container, passenger vessels. I worked as British operator for a year, but 3 months training as a pilot. Now I'm working as teacher assistant in the University of Jeddah. I'm doing my PhD in traffic light.
Good. Enjoying it?
Yeah. So far so good.
My name is Saleh. I'm from Saudi Arabia. I have qualification of your second officer, your PhD from Singapore. Also bachelor degree in nautical science from Singapore University in Jeddah. I served on board several types of ships, chemical tankers, oil tankers, LPG, container, store container. I worked as a yard and vessel planner and container terminal. And after that, I worked as a teaching assistant in my university, in W University. And right now, I'm completing my PhD degree here at Starflight.
Hey, my name is Volkan, and I graduated as a naval architect and marine engineer from Istanbul Technical University in Turkey. And now I'm doing my PhD on human factors and the maritime safety culture.
Okay.
So far,
previously? You know,
No, I don't have like I'm an engineer, shipbuilding engineer.
Yeah,
Like,
yeah.
I have been in like shipbuilding,
Shipyard.
etc. And but I don't have any seafaring experience.
That's okay. We take people without seafaring. Yourself?
Chico. My name is Chico from Nigeria. Maritime Management Technology, like business, maritime business. I have the experience as a teaching maritime academy of Nigeria. I'm here doing
Good. What do you teach?
maritime business.
Maritime business.
I'm just teaching.
Just what? Maritime law or just maritime business?
Chief Operation and Management.
Okay.
More focus on the commercial aspect of naval system.
Okay.
Including insurance, maritime transport, and corporate maritime strategy.
My name is Manjari from Turkey, and I graduated from Istanbul University. My department is Marine Transportation Management Engineering. First, I worked as a ship agency on the land in Istanbul. Now I'm going to my Istanbul University in aviation on LNG process.
So what makes you interested in LNG?
Future of fuel energy. Yeah, oil price is good.
Yeah. There's quite a few variables. If gas is competitive in price, it's a very clean burning fuel compared to residual fuel. So from the point of view of emissions and it's a low sulfur fuel, a low sulfur alternative, it's a very good fuel. Also, the interesting thing as well is that the amount of residual fuel left over from the refining process is now each year it's less. So if you take a barrel of crude oil 10, 15, 20 years ago, maybe 20% of that was left as residual fuel. Now with the techniques that they have in the refining process, the amount of residual fuel remaining is less and less because the drive is for the distillates, the better quality fuels, and the more that can be withdrawn or extracted from a barrel of crude oil, it means that the less residual fuel that is there. So if there's less residual fuel in the market, the price of it is quite high, and we're looking at alternatives, obviously, and if the price of gas is favourable, then it makes a very attractive marine fuel. Now, the bit I want to talk about now is propulsion. Can I get this on the screen? Yeah. There's a change from here. No, it's this thing here is what's on the change is this one.
So, you'd like to use this one?
Yeah. Is that all it is? I can get you copies of these protocols afterwards. Okay. LPG, liquefied petroleum gas, tends to be propane and butane. These have been transported around in ships for a long time, and they have not. This type of gas doesn't normally boil off, because its temperature is minus 43 degrees. So being minus 43 degrees as a liquid, we can re-liquefy it. We use a refrigeration cycle. We can use a Freon, or we used to use Freon based. It's a different refrigerant now. But we use a primary refrigeration cycle that cools down the boil-off gas. You understand what I mean by boil-off gas? Have you been introduced to this before, or is this your first lesson on LNG? This is your first lesson?
No.
Were you guys?
Yeah,
First lesson. Okay. Do you understand that one of the properties of methane gas, natural gas, it boils at a temperature of minus 162 degrees centigrade. That's its boiling point. So it will not remain as a liquid at atmospheric conditions. It boils off, and it produces a lot of gas, turns into vapor. So the problem we have with this gas is keeping it contained. Containment is a huge issue in LNG ships. LPG ships, this is LNG. LPG minus 43 degrees centigrade. So minus 43, we can re-liquefy that boil-off gas. The gas that boils off, we can pipe it back, we can compress it. If we compress it, we can condense it back into a liquid, we can return it back to the tank. So there's no wastage. The boil-off gas, which will naturally occur anyway, because no matter how well we insulate the tanks, heat will always go in, ambient heat will always go in there and cause the boil-off to occur because it's at minus 43. So with the LPG, it's very easy to compress it, condense it back into liquid, return it back to the tank. Now, because of the nature of LNG and the temperatures, the re-liquefaction process to be carried out on board ship is a lot more complicated. It involves higher pressures, it involves multi-staging, it involves more equipment, it involves higher power, electrical powers. So it's not been, up until recently, it's not been normal to re-liquefy on board. This is what an LNG ship looks like, with the hemispherical, spherical tanks in this case. Obviously, if we're containing a liquid, a sphere is a good shape in order to be able to resist the force of the pressure that's in it. If we have a tank and it's got liquefied gas in it, and this is boiling off, then it wants to exert a pressure around the tank. Now, in order to contain that pressure, we would have to make the thickness of the tank, the shell thickness would have to be very substantial. That would add to a significant weight. Weight of a ship causes it to sink lower in the water, which means you carry less cargo. On smaller ships, you can pressurise the gas and keep it under pressure or semi-pressurised conditions. That's a membrane type of tank. But if we just quickly, before I go on to propulsion systems, we'll just look at what happens inside an LNG tank. This is a stainless steel membrane type tank. It's a sort of helical shape. It can't withstand a lot of pressure. It can't stand a lot of pressure. So as boil-off occurs, we have to remove the boil-off gas from the tank. It can't stay in the tank. So LNG, methane gas, got a number of substances that make it up and different volatility, which causes it to evaporate. The heat flows always from a hot place to a cold place. So even ambient outside temperature, even today in Glasgow, the heat will still flow into this tank because it's at such a low temperature. Now, the surrounding tank is surrounded with insulation, try and retain as much heat as possible, and we usually have air spaces and ballast tanks around the outside, and to try and minimise the heat that's going into the tank. So that heat creates the boil-off gas. Boil-off gas, we need to remove it from the tank, otherwise the tank will overpressurise, and that's dangerous. So we can lose about 0.1 to 0.15% per day of the cargo in the tank boil off. Now, we can't vent it to atmosphere. Why not? 3 reasons why we can't really vent it to atmosphere.
Dangerous?
It's dangerous, it's flammable. It's also not environmentally friendly, up in the atmosphere, it would be ozone depleting. And 3, it's a valuable commodity. It's a waste. It's a waste of cargo. It's a waste of money. Somebody had to pay for this. So the rate of the boil off depends upon the heat into the tank. The more heat going into the tank, the faster the boil off process takes place. The operating pressure in the tank, if we can actually make the tanks, if we had a small vessel with a tank on, we could keep it under pressure. Think of your domestic tanks that we have, bottles for barbecues and things like this. We use for patio gas and things like that. That's liquid under pressure, but it's such a small diameter that the thickness of it is capable of containing the pressure at ambient conditions. But the bigger we go, as I say, the wall thickness has to increase, which adds to the weight. Sailing conditions during a voyage as well. If the weather's rough and the tank's being agitated, the liquid's all splashing around, that tends to increase the boil off as well. And then the LNG loading and unloading operations. So what do we do? LNG. When they first started transporting LNG around, the boil-off gas, what do we do with it? Can't release it to the atmosphere. We'd have to, if you look at offshore platforms where they've got gas, they've got a flame, they burn off, any boil-off is just getting burnt. So we can't do that. So they devised the idea of taking the boil-off gas and putting it back into the ship's engine room, where it got burnt in a boiler, or a pair of boilers. Usually in a steam-driven ship you got 2 large water tube boilers. And that steam that is generated drives a turbine, which drives the propeller, which drives the ship. So now this boil-off gas, this byproduct of the heat going into the tank, instead of being wasted, we're actually getting a very good resource out from it, because it's driving the propeller, it's driving the ship. So it says here LNG carriers but only steamships remaining. Maybe not quite true. There's the Waverley, if you want to go for a paddle steamer on the flight. That's steam driven.
So in this case, they use LNG as a fuel in a non-LNG driven vessel. It's almost impossible. It's like you need to store they came out of LNG, then
You have to have it in a pressure vessel. If it's a non-LNG tanker, for example, then what you'd have to do for a dual fuel engine is to have a receiver, a tank, a vessel that's capable of holding a quantity of liquid natural gas. So you're going to use this. So you would need to put, it's like having a fuel tank. So you're going to need a circular fuel tank or a cylindrical fuel tank on board the ship to fuel your engine. A number of years ago, the UK government had an initiative, and I'm sure they do it in other countries as well. In Australia, for example, a lot of the taxis, they run on natural gas. They've got a cylinder. They've got a cylinder in the boot of the car, in the trunk of the car, and then it can be dual fuel. You can start it up on petrol and then change it over onto gas. But again, because the cylinder diameter is quite small, it's capable of taking a charge of liquid gas. Now, that might give you a range of 200 miles or something like this, I don't know. But on what they're talking about now on new ships is future-proofing them by having putting an LNG tank quite close to, so if you've got, if the ship is, say, like a container ship, for example, it's not a gas carrier, the container ship will contain injection. Yes, sure. Then we're talking about putting somewhere near the end of space. We'd put a liquefied gas tank, so a pressurized vessel with liquefied natural gas, and that's what would be getting used to burn in the engine. But the engine that we're looking at are diesel engines that are what they call dual fuel. I don't know if are you familiar with that concept? The dual fuel diesel engine, it can burn either marine diesel oil or residual oil and gas at the same time. But if it uses fuel oil, it uses fuel oil as a pilot burner. So the fuel oil is the igniter, if you like. It will ignite the gas. So I'll show you a video of it in a minute. Whereas with using the gas in a boiler, we can use gas on its own. We can use a mixture of with a dual fuel burner in the boiler. So we mix gas and heavy fuel in the burner. So yeah, if we're going to carry LNG as a fuel, then it needs to be kept in its own pressure vessel. So there will be no boil off or anything. The boil off only applies to cargo, because you think of the tanks now in an LNG ship, you're looking at around about 175,000 cubic meters. That's how much cargo you have on a big gas carrier. Now I believe that it's not the Saudis. There's some shipping companies that is building them bigger. It's going to build them bigger than 200,000 cubic meters. So that's an awful lot of liquid and gas in there. So there'll be a lot of boil off coming from this. So traditionally, when these ships first started, then the boil off went back to the engine room. And this is the type of boiler that the gas and fuel would be burnt in. It's a large roof-fired boiler. It's got a big combustion chamber here, and it can modulate on fuel oil or gas or both. So the fuel gas mixture comes in through the top. You've got a long flame That the heat from the gas passes through superheaters and economizes, and then goes to the exhaust up to atmosphere. Now the steam that's generated is what we call superheated. So in the steam drum, where we have a mixture of water and steam, we get what we call saturated steam. So saturated steam is the steam which is changing phase from water to vapour at a certain pressure. Now we all know that at room temperature water is boiling at 100 degrees centigrade. Yeah. In a large boiler, and these boilers operate at 60 bar pressure, and the saturation temperature is 273 degrees centigrade. So that's the boiling point at 60 bar, 270 degrees centigrade. So the water won't boil until it gets to 270 degrees centigrade. So all that heat is being liberated from the burning of the fuel is changing the water to steam at 273 degrees centigrade. Now that steam is essentially what we call wet. It's saturated steam. We can't put that into a turbine, because if we put it into a turbine, some of that steam will start to condense as it passes through the turbine. Condensing steam passing through the turbine will cause impingement and erosion on the blades and damage. So we therefore have to take it way beyond this temperature here. We take the saturated steam out of the drum, pass it through a couple of superheaters. A superheater is an external heat exchanger from the drum that takes dry sensitive steam from the drum and then passes it through a series of elements with the hot gases passing over it. And we have a control system built in, so we regulate the superheater temperature at about 525 degrees centigrade. So that's to the turbine. So put the turbine at 525 degrees centigrade. Now, because it's steam now superheated at 525 degrees centigrade, there's absolutely no liquid at all in it. It's just acting like a gas. It's like a dry vapour now that's going down and passing down through the turbine. It passes down through the turbine, acts on the turbine blades. The turbine drives the gearbox drives the shaft drives the propeller. So that's the whole frame of the steam plant. Now, I like steam plant because it's all thermodynamics. It's like it's a heat balance. It's the trouble about the steam plant is its efficiency is not fantastic. The boiler efficiency is very good. The turbine efficiency is very good. But the big problem is in a steam plant, what do we do with the steam after it passes down through the turbine? We expand it down from 60 bar and 525 degrees centigrade down to negative pressure. We take it down to a vacuum down at about 45 degrees centigrade. So it's gone all the way from 60 bar, 525 down to a vacuum as it leaves the LP turbine. The huge Achilles heel, the huge problem in the steam plant is we've got to recondense that steam to get it back in the boiler. We can't pump steam. Plants steam if we try to, low pressure steam if we try to pump it, we just compress it. So we've got to condense it to get it back in the boiler. That's where the big loss is in the steam plant. Are you familiar with the TS diagram? Temperature entropy diagram? Have you ever seen pH diagram? Pressure entropy?
Very interesting.
Very
interesting.
Right. Essentially, without going into it too deeply, essentially what the heat that is, and we're talking heat and energy, heat in kilojoules per kilogram, that's created, that goes into the steam, to give it its entropy. Its entropy rises as it gets higher temperature and pressure. That entropy does work in the turbine, and the work, entropy kilojoules per kilogram times the mass flow of steam going through in kilograms per second gives us kilowatts. Is the actual power. So that's the power that we get out of the turbine. So we can have 30,000 kilowatts at the propeller, and we're getting that power from the steam. Steam's getting its energy from the heat coming from the gas or the liquid fuel that we're burning. Now, stop me if I'm going too fast, or ask any questions about it. Yeah, just say, yeah? Okay. To give you a size and scale of marine boilers, they're pretty large, large furnaces. In the old days, the furnaces tended to have the burners going in at the side, horizontally fired. Nowadays, they're roof fired. The roof fired in a large furnace gives a longer, what we call dwell time. So what happens is the heat from the combustion has to get absorbed by all these radiant tubes. And they're absorbing the heat, and the tubes inside contain water, which are obviously turning into steam. And circulation is very important, passing through the boiler. What you have is a series of riser tubes. So as the tubes absorb heat from the furnace, what happens is bubbles get created, steam bubbles get created, so the water gets less dense, so it tends to rise up the way. And then we have large bore external downcomers, which are bigger bore pipes, and they contain much more dense water because they're unheated. They come down like this. So the density of this water kind of forces circulation. So the boiler relies on natural circulation taking place. And the saturated steam generated passes through a superheater and then through the superheater to the turbine. This shows you a couple of boilers being installed on the ship. This is the steam room. That's these external downcomers I was talking about. The large bore downcomers. They'll give you the circulation. This is inside boiler, it's piping tubes. Again, just showing what happens. The heat creates circulation in the boiler, saturated steam gets by the superheater, and you get superheated steam to the turbine. And that's just a feed water system. And the water in the boiler gets turned into steam and superheated, passes down to the turbine. This is where the big loss is in the condenser. A lot of heat, all the heat that's been generated in this steam, it's now we extract as much as we can, work out of it in the turbines, but the trouble is it now goes into the condenser. In the condenser, we're down at 45 degrees, and we have to get it back up into the system, back into the boiler again, and that's done by pumping it. We have various heat exchangers on the way to try and improve the thermal efficiency of the plant, and try and get the temperature as high as possible before it goes into the boiler again. The higher the temperature is going in the boiler, then the less fuel it needs to flash it into steam again, so that makes it more efficient. Okay. Now, turbines very simply use a nozzle and act on blades. theoretically there's two types of now, an impulse turbine and a reaction turbine. A reaction turbine is where you get a kick from steam goes into the a nozzle and it gets a kick effect. You know those things you might have had as a kid you can blow on with a windmill type thing. That's like a reaction turbine, whereas an impulse turbine is the nozzle acts on blades. Now if we take high pressure steam from the boiler at 60 bar to 555 centigrade and we pass it through a nozzle and it takes a huge drop in pressure of the first stage nozzles. What happens is velocity increases, yeah, so you get high velocity, very dry, super steam impinging on the blades. And so that's now doing work. It's dropping from a high pressure to a lower pressure, doing work on the blades, it's driving the turbine. As you can see from here, that's quite a complex diagram, just showing the stages of the blade and the bearings either side. I won't linger on that too long. Suffice to show that in the turbine it consists of rows of moving fixed blades. The moving blades are all keyed onto the rotor, which is turning, and then fixed blades fitted into diaphragms, which are fixed into the turbine casing. And all the fixed blade do is direct the steam at the correct angle onto the next row of moving blades. So the blades are curved, so the work's done in this first stage of blading here, driving the turbine, and then this blade is directed onto the next step, and so on. So essentially, that's what's happening here in a turbine. You've got moving, fixed, and moving blades. And what happens as the steam passes through, its volume, it's expanding all the time. So the blade sizes get bigger as we go through the turbine. It's the same as any turbine, it's the same as like even a gas turbine, a turbine you get in an aircraft or whatever. As it goes through the stages, it gets bigger because the blades get larger. The blades are feed onto the shafts, and they're got to be very strong to stand the forces that are put on them. And because the turbines operate at the most efficiency at very high speed, so turbine speed is maybe 7,000 RPM for a high pressure turbine, and about 3.5, half that for a low pressure turbine. The propeller is efficient at very low speeds, maybe only about 80 RPM for a single big multi-bladed propeller. So we need a large gearbox, a large reduction gearbox, and all that gearbox does is reduce the speed. There's no changing of gears. The gears are what we call a lock train. They're locked together, double helical gearbox. And so you can see, this is a turbine plant here. First turbine ship I ever went on, it was a very large vessel, and you get into the top of the engine room and you look down, and normally on a motor-driven ship you can see this great big engine. On a steam turbine you look down and go, where is it? And this is the HP, this is the LP turbine here. So this is down in the bottom of the machinery space. That's the steam pipe going into it. The high pressure turbine is this little thing here. This is the high pressure turbine.
That small box is
yeah, that's developing at a tremendous amount of power. This the high pressure turbine, and that's the low pressure turbine. You can see that they're both going to a common gearbox. They both have output shafts and going into this very large gearbox which goes into a single shaft and drives the propeller. So in terms of maintenance, the turbine is very, very, very reliable. If you think about it, essentially, although all the blades are fitted round to all the discs, it's essentially just one moving part. It's just a rotor that's rotating. okay, it's supported in bearings and lubricated and cooled. It's got a thrust bearing that locates it in its casing. But essentially, it's pure torque, it's pure rotary motion. Not like a diesel ship where the pistons are going up and down, you've got large reciprocating masses, out of balance forces. On a turbine ship, this is why the old passenger ships from years ago, when they used to cross the Atlantic to see who could be the fastest, all the famous liners, the Queen Mary and the USA, the famous French and Italian ships that used to see who could be the fastest. They had turbine-driven ships, so very, very smooth from the passenger's point of view, and the accommodation, there's very little vibration, because all that's happening is you get pure rotary motion, pure torque, and there's no vibration passing up through the superstructure and accommodation. So from that point of view, very reliable. These steam turbines, you don't touch them, provided you've got correct water treatment. And the water treatment is really, really important to the boiler. The purity of the water is very carefully controlled, so that the steam we get, as I said, it just behaves like a very dry gas. The steam, there's no impurities carried over. As long as that happens, your turbine will remain in excellent condition. And what has been happening in recent practice is every 5 years in a dry dock, you would open the casing and have a look inside, just a visual inspection. Now they don't even do that. Provided you take vibration readings and you take a history of vibration readings and other parameters, the temperatures, oil samples, etc., from your bearings. They don't even, the surveyors now, like people like Lloyd's and PNB, they'll say, okay, you don't need to lift it up, you don't need to look inside, we know it's really good, because we'll take the vibration history. So it could go for 7 years without even looking inside. If you look at a diesel engine, how often are you going to look inside that? So from a maintenance point of view, as an engineer's point, this is very good because it's almost maintenance free. Whereas with a motor ship, diesel engine you're always doing maintenance, and you're always renew valves, etc. So the two things kind of outweigh each other. So these were very fashionable. Steam turbines were very fashionable years ago because they were the only things that could develop high powers. The engine makers caught up and they started building bigger engines. Steam then went out of fashion because of the high fuel costs, which is associated with the condensed steam again, which lowers the plant efficiency. So the steamships almost died off. They stopped building steam-powered tankers, oil tankers that is. And then all of a sudden, when LNG came to the fore, then the steam made a big resurgence again because it was the ideal vehicle to burn the boil-off gas. So that's steam plant from LNG point of view, and why steam plant is now back in favour. Although now what's happened is the engine builders, they've built dual fuel engines that can burn LNG too. So I've got a little film here that you might find interesting.
So normally the cost of the steam turbine is cheaper than the diesel engine, or?
Initial cost? There's not much difference.
The maintenance is better.
Maintenance, definitely. Much less spare parts, much less man hours in the maintenance side.
Okay, why they didn't apply all the ships by
cost? Cost, yeah. Because this thing I was saying to you, the if we draw a diagram of what happens in the steam plant, and if we plot temperature, we've got two curves here, and this is S entropy. Then in the steam plant we take water and we heat it up to pressure at 60 bar pressure, so 270 degrees. And then it changes from water to steam. This is the saturated liquid line, this is saturated vapor line. Once we get to 100% saturated vapor, we superheat it, so the temperature rises up to 520 or so. Everything's good up until now. We now expand this down into the turbine. As it does work in the turbine, it drops the temperature and pressure, and it now hits the saturation line. When it hits the saturation line, it starts to get liquid in it. So it means that the last blades in the LP turbine, they get damaged because of erosion. So we have to put a thing called stellite. Stellite is a very hard-wearing material that gets bonded onto the blades so they can cope with wet conditions. So why do we want wet conditions? Well, we want to take the temperature down as low as possible. So we actually go below atmospheric conditions. We create a vacuum in the condenser so that we try and expand the steam as much as possible. But however, under this diagram, this is equivalent to the work done in the turbine. All this is the work done in the turbine. This is the heat loss. That's the heat loss to the condenser. So all this is very efficient until we get to the condenser. The condenser, huge amount of heat gets lost to the cooling water. Now, on a ship's condenser, it's seawater cooled. Seawater, it's a single pass condenser. Seawater comes in one side, goes out the other side, and that condenses the steam into water again. We can now pump it. Now that it's liquid again, this is liquid line here. We can pump it back up into the boiler again. So that, if you knew how to get that steam back into the boiler again without that big heat loss, you'd be sitting on a beach in Barbados now for the rest of your life. Winning a Nobel Prize. Yeah, winning a Nobel Prize. You have to defy physics. You have to get that this low pressure steam. It's now exhausted. In the literal term, we've passed it down through the turbine. We've got as much work as we can out of it because we've actually expanded it down to a vacuum, and as we expand it, its specific volume grows. So therefore, the LP turbine, the blades are much bigger than the LP turbine because, in fact, the LP turbine blades are about this size. The HP turbine blades start with this size, and because it's low pressure, like a big windmill, we're trying to get as much work done out of it so that it can drive the ship. But this is the Achilles heel of the steam plant. Now the engine builders, they quickly cottoned on to this and said, okay, we can build our engines bigger, we can build them as big as your turbines, we can produce as much power as you can. But there's a cost. It takes more spare parts and it takes more man hours. Now you're the crew aboard the ship, or you're the engineers aboard the ship. You're there anyway, so the company expect you to work and fix things, yeah? You're an asset, you're there to do the maintenance, and then they'll pay for the spare parts. If the cost of the spare parts outweighs the fuel that they're saving, then they'll go for the cheapest option. That's what shipping companies do. Yeah. You know? And if you've got a fleet of ships and you can save 10% of your fuel bill on every single ship, then it adds up to a lot. So even if your initial costs are roughly similar between a turbine set and a diesel engine, the ongoing cost of the diesel engine is going to be more, but the fuel costs are less.
Does it include the same efficiency?
No, that's what I'm saying. The efficiency for a diesel engine is more. Yeah. But even then, the diesel engine efficiency is not that great. It depends what fuel it's burning, but it's probably about getting 45% or thereabouts. Now, in the boiler, you're looking at temperature, efficiency of about 88% in the boiler, efficiency of about 90% in the turbine. Because of the condenser, this reduces the overall steam plant efficiency to about 32%. So the amount of heat that we're putting in, for every say $100 we put in, then $32 or $70 are wasted. Although we get a very good plant. The other things with modern diesel engines is they've used the exhaust for like heat recovery, to use the exhaust to distill water for the freshwater plant on board, for the passenger cabins and stuff like this, and also economizers to generate steam for heating for other purposes. So they've managed to cleverly use the exhaust from the main engine, or the diesel engine, in order to extract the heat that's recovered from that instead of it going to atmosphere, which has created a better efficiency in the diesel plant. But there's still companies are building steam-driven LNG carriers, because the steam is proven when it comes to LNG and the using the boil-off gas. It's been used for many years. It's proven technology.
But except LNG driven vessels, do you know any company who are still planning to do investment on steam engines, or except LNG stuff?
No. Unless you've got the boil-off to burn, it's not. There's no economic case for it.
Like a Navy, I think. Some warships, they are using steam engines still, and they.
Yeah, but they've got nuclear reactor. Yeah. If you're using submarines, you go down to Faslane Naval Base here. This is near where I live, and you have nuclear submarines. They use steam power. They use steam turbines. As I said, the steam turbine is very small. It's very compact. It's got a very high power to weight ratio. It's very efficient on its own. It's very efficient. If you've got a nuclear reactor and you've got a jacket around the nuclear reactor, and this is boiling water to provide steam to give to the turbine, then you've got a almost endless supply of fuel. You don't need to stop every 2 weeks, 3 weeks, get some more fuel added to burn. You're not burning residual fuel. You're not burning fossil fuels and anything like that. You're not burning expensive fuel. You've got a reactor there, a nuclear. I mean, the British are building 2 aircraft carriers now, and they're not putting nuclear power in, they're putting conventional power. They'll be very expensive. Now, a lot of these Navy ships, they use gas turbines. Steam turbine takes about 3 or 4 hours to warm up. See, if you've got a cold steam turbine, you have to admit the steam in very small quantities, and you have to have the drains open, you have to turn it so that it all heats up very evenly, and it takes a while because of the high pressures it operates at, and the turbine casings are really thick, because of the 60 bar pressure inside, and the turbine flanges and casings are very thick, so you have to warm it up very slowly. However, a gas turbine, like a jet aircraft, a gas turbine can be started up very quickly. So a lot of Navy ships use gas turbines because they need to react fast. If you're a patrol boat, or you're a destroyer, or something like this, and the enemy's appearing, you can't say, well, we'll be ready in 4 hours time, we're just going to warm up the steam turbine. So they need instant, reaction, so they use gas turbines. But gas turbines for use on board ships are very inefficient. It's very expensive to run a gas turbine on board a ship. So unless you're the Navy, where the taxpayer is paying for, they're paying for your fuel. Yeah, they don't care. Yeah, you're not a commercial company anymore. You don't have to make a profit. You don't have shareholders. You don't have this sort of thing. So it's okay for them to have gas turbines and instant, put them on, away you go, 23% efficiency, something like this. But they can go very fast. What some of them do actually is they have a combined cycle. You can have a gas turbine and a steam turbine. So if things are easy, you can slowly get the steam turbine up, go and move along at a cruising speed. Then if you need to go really fast, you can kick in the gas turbine as well, give you extra power. I mean, aircraft obviously use gas turbines because there's no way you can take off with a boiler and a condenser and all the steam plant on tight wings of a plane, because obviously the gas turbine has got a very high power to weight ratio. For something that's very small and very light, it produces enormous power. I suppose from a plane, from an aircraft, once an aircraft gets up cruising altitude, its fuel consumption is minimal then. It's just to take it up. It's still the most efficient way of flying. But yeah, if I was to build a ship, I probably would not have a steam plant in it. What the traditional layout for a ship was to have a big diesel engine driving the propeller. Single engine, slow speed. The engine turns the same speed as the propeller, big direct drive two-stroke. Nowadays, a lot of cruise ships, even big container ships, etc., they start to go into a diesel-electric outlay, or diesel-electric layout. So rather than having one big engine supplying propeller, and this takes up a lot of space. If you're a passenger ship, for example, then you want to use that space for passenger accommodation, for atriums, for this and that. So you're better off having like a load of small engines that drive electric generators. So then all that electricity generated can be sent back up. And a lot of them now, instead of having a propeller, it's podded propulsion. So we've got pods that are steerable pods, so we don't need rudders, we don't need steering gears. So we can make the layout of the vessel much more flexible by having lots of small engines generating electricity and using electric motors. Certainly in the cruise industry, that's the way they are nowadays, and then they use high voltage as well, 6.6 kV, 6,600 volts. Is normal now for the apply for the electric motors because it keeps the current down. The higher voltage you go, keeps the current down, keeps cable sizes down, costs, etc.
So, anyway, after 6 years, we will just like, we will have an engine, we will start discussing about, now we install nuclear power, that is in then after nuclear, we will
The trouble with nuclear, it's so emotive. It's so controversial, nuclear. If you've got a nuclear powered aircraft carrier, like the USS have, the Nimitz and things like this, they can cruise around the world, go to various places. Some countries welcome them, some countries don't welcome them. If I've got a nuclear powered oil tanker or gas carrier or something like that, there are a lot of places in the world where they say, no, we don't want you here because you're too much of an environment or ecological hazard or not even ecological. The nuclear explosion, it's radiation, it's death, you're going to kill people. And so that's the trouble commercially, I think, trying to have a commercial nuclear powered ship is you'd have to be able to trade where people would accept you. They will take you alongside, you can discharge your cargo, you can sail away. And once the local residents that live near the berth know that you've got a nuclear, they'll be protesting. You won't get in. So it's but you're right. I mean, it's just the way things happen through history. We're always looking at alternatives. Just now, gas is a big alternative, and one of the reasons is that a lot of this shale gas, a lot of fracking and stuff is going on. If we can get cheap gas, then that'll keep us going for maybe another 50 years. Plans in 50 years' time won't be a problem. some other young engineers will be looking at it and saying, well, what can we do now? Now that we've run out of fossil fuels, we're running out of shale gas, what have we got left? Solar power, renewables,
like biofuels, some veggies.
Yeah.
What would the maintenance be like? This electrical system?
Sorry?
The maintenance kind of would be more expensive than the diesel. For the electrical system.
Yeah, well, it's driven by diesel. It's diesel engines.
Diesel engine,
Yeah.
the normal propulsion system.
No, it's because of the flexibility of the layout. You're looking at passenger ships. Passenger ships maybe have 4,000 or 5,000 people on board. These cruise ships, so they've got a large amount of people on board to look after all the equipment, and commercially they're making a lot of money, so they can afford it.
Oh, but if you have to use it to
Oh, if you would use. Yeah, well, you can. There's so many layouts nowadays. You can use boil-off gas to burn in a diesel engine. The diesel engine drives an electric generator, which creates electricity. The electricity drives the electric motor. Electric motor drives the propeller. Yeah. See, every time the steam turbine people come up with some, people, Japanese, Kawasaki, Mitsubishi, very, and Star Laval are the sort of biggest turbine manufacturers. They come up with a new system, more efficient turbine plant, reheat boilers, then the diesel engine people kick back and they come out with something. And this is okay, MAN BMW. Have we got volume?
Yeah. Volume.
Yeah.
In the coming years, global shipping will be facing tough challenges. Growing energy demand is pushing up liquid fuel prices, and the use of alternative fuels becomes ever more attractive. In addition, rising environmental awareness leads to stricter emission regulations, especially in the IMO emission control areas. In the future, these areas will be restricted exclusively to ships that fulfill the IMO Tier 3 emission regulation. To meet these challenges for tomorrow's shipping industry, MAN Diesel and Turbo presents its new fuel-flexible 4-stroke medium-speed engine that can be used for all applications, as a main engine for diesel mechanic propulsion, for diesel-electric propulsion, or as an auxiliary engine for onboard power generation. The MAN 3544DF. Its dual-fuel technology, with 2 separate injection systems, makes it run on any fuel available, no matter if it's liquid fuel such as heavy fuel oil, marine diesel oil, and marine gas oil, or gas fuel like LNG. The 3544DF is based on MAN's well-proven 3244CR engine. Both engines feature a state-of-the-art common rail system with injection pressures of up to 1,600 bars. In diesel mode, this system and other technologies enable a 3544DF to fulfill the current emission regulation IMO Tier 2. To meet the even stricter emission limits of future regulation IMO Tier 3, the 3544DF can also operate in gas mode. Switching to gas can be done on the fly at loads between 15 and 100% with no loss in engine power. To ignite the air-gas mixture, a small amount of liquid fuel is injected by a separate pilot fuel system. In gas mode, the MAN 3544DF fully complies with IMO Tier 3, lowering CO2 emissions by 20% and other emission levels by up to 99% and beyond, compared to liquid fuel operation. In addition, using gas as fuel also provides substantial economic advantages. Over the past years, the price difference between liquid and gas fuels has increased steadily and is expected to keep growing. As fuel makes up the largest part of ship operating costs, reducing fuel expenses is the most effective way to keep shipping affordable. Already now, using natural gas as main fuel enables ship owners to save fuel costs in a double-digit percentage compared to a conventional diesel engine. When looking at total operating costs, the savings potential becomes even higher. The MAN 3544DF allows ship operators to fully harness this potential, plus the flexibility to switch between fuels at any time for optimum resource utilization. For sustained operation on a wide range of gas qualities, the 3544DF features a fuel sharing mode. In this mode, both gas and diesel supply systems are active, which lets the engine run on multiple ratios of gas and liquid fuel. This makes the 3544DF virtually immune to variations in gas fuel quality, allowing it to operate even on gas that would be unusable for a conventional gas engine. Highest power output in its class, compliance with IMO Tier 2 and Tier 3 without aftertreatment systems, low operating cost due to affordable gas fuel, complete fuel flexibility, a robust design based on proven engine technology, the ability to upgrade IMO Tier 2 compliant 3244CR engines to dual fuel operation entirely on board, and an increased vessel resale value due to an engine that fulfills all regulations for many years to come. All this makes the MAN 3544DF the perfect choice to keep cost of ownership down and give ship operators the flexibility and sustainability they need. With the 3544DF and the larger 5160DF, MAN Diesel and Turbo offers its customers a complete range of fuel-flexible four-stroke medium-speed engines that fulfill all economic and environmental demands of tomorrow's shipping industry today.
Now that was an advert for MAN, and that was just to let you see how many companies were where the students can download this video because of the discussion. Right? There's a question in this pandemia, so where can the students can download this video? It's on YouTube. Alright, I've got it. You want a link for it? Yeah, you can. Or the title or something.
The name of the video can be easier.
Yeah, the name is Man MEN L35/44 dual fuel engine.
In the coming years, global shipping will be facing tough challenges. Growing energy demand is pushing up liquid.
That was basically just to show you what the engine builders are doing to compete. But you've seen a boiler, right? Do you know what a boiler burner is? It's a set of fixed orifices. The fuel passes through the boiler burner. It's arranged so that it creates a spray or a pattern that mixes with air very efficiently. Normally the fuel swirls in one direction, the air swirls in the opposite direction, so the two of them are mixing very quickly, very intimately, and combustion is as rapid as possible. But there's no moving parts as such. It's the same as my turbine. But you look at the diesel engine, how complicated that is with the pilot fuel and then the gas being injected, and it all has to be timed, and then the timing has to be maintained, change switch after a while, electronics sometimes are not so reliable. So it goes down to you as a ship owner. If you're the ship owner, what do you want? Do you want to go with what's proven? Do you want to know what this LNG ship has been sailing around with a steam turbine plant for years, and it's reliable, it's very reliable. Do you want that, or do you want to go for the cheaper option, fuel wise, which is the diesel engine? But in looking at what we talked about earlier, non-LNG tankers, they will still have to carry diesel fuel, but they will also have to carry, as I said, a cylinder, a tank, pressurized tank full of liquefied gas to be able to use in the engine. That's what we'll be supplying that engine there, that MEN engine.
For the LNG and LPG, they are charging the cargo. Commodity with the fuel, they are using the water from the cargo to raise their engine.
They still have some.
Keep some amount of
still keep some liquid fuel on board. Yeah.
In the same tank, the cargo tanks, or in the tank?
In the cargo tanks.
In the cargo.
Yeah, because what happens is, in an LNG, I'll show you this. I've got some presentations on this too. In an LNG carrier, they always have what they call a heel, and that's the amount of liquid that is retained in the tank. And because if we don't keep liquid in the tank, then if the tank becomes empty, then the tank will warm up, and the tank then needs to be cooled down again. So it's what you can have. I'll show you this. Show you this later. But you can pump your cargo to a pressure vessel and keep it on board, and then you can sail on a ballast voyage and allow the tanks to warm up. they remain empty if you're in a balanced voyage. Particularly if you think that one of the or two routes for gas carriers, Brunei to Japan. For years, Shell were taking gas from Brunei to Japan, also say from the Arabian Gulf to Japan. Japan is a big importer of LNG. If you're carrying LNG, say from Brunei to Japan or from the Gulf to Japan, you get there with a full cargo of gas, you discharge it, you're coming back, you've got nothing in the tanks coming back until you go back to the loading port, but you keep a small amount on board so you can cool the tanks down. So you pre-cool the tanks before you go. You can't take a new cargo on board. If your tank is at ambient temperature, 25 degrees or something like that, you can't take liquid at minus 160 into that tank. Thermally, it's going to stress it too much, so you have to cool your tank down to the correct temperature before you can start taking cargo on board. I've got that. I can show you that in the presentation after. Are we stopping for a quick break or something like that?
Yes, please.
Yeah, do you want a coffee break or something just now? Okay.